All right, we're going to be in section 6.1 to start off with, the nth roots. And rational exponents. All right, nth roots, we're talking about not just square roots, but cube roots, fourth roots, fifth roots, that sort of thing. Higher degree of that. An nth root, square root, it looks like a square root symbol, but there's going to be a number right there. Square roots, they never write a number there. It's an imaginary, it's like a 2 there when it's a square root. We're going to deal with cube roots, fifth roots, that sort of thing as we go through this. And so that's, I'm going to refer to that as an index. So if I say what's the index, I'm talking about what's this number right here. That's the nth part of the root. The index is the nth part of the nth, the end of the root there. Okay. So we're going to work with this. Non-calculator and then with calculator as well. Need to be able to do it without a calculator so we can understand how to simplify, especially those that have variables involved as well. So understanding what's going on is also there. Find the nth root of A. Example A. N is 3. A is equal to negative 216. So this is how they're going to present the problem. What they're asking you to do is find the third root, or the cubed root, same thing, of negative 216. All right. So when we're doing nth roots, whether it's an odd or even number is important. If it's an even number, then you can't do a negative inside. If it's an odd number, you can. It's okay. So here we got an odd index of the 3, so it's okay to have a negative inside. That stems back to when we were doing square roots, and you had a square root of a negative number. That's where the complex number system came in. That's a square root is an even index, so that's why we shy away from negatives inside of the even indices there. So here we've got a third root of negative 216. So what we want to get here is think about how we did square roots. We did factor trees. So with this, we can do factor trees with 216. I know 2 goes in 216 108 times. I don't worry about the negative until the end. And then 108, I know something about that. That's 9 times 12. Right? And that's 3 and 3. That's 3 and 4. Now, here's where the nth root, the index, comes back. When we're doing square roots, we look for pairs, sets of 2. Here we're doing a cubed root, so we look for sets of 3. Okay, so there's 3 3s right there. And then there's 1, 2, 3 2s. So there's a set of 2s that comes out and a set of 3s that comes out. That's 2 times 3. The answer is also going to be negative because it was a negative inside. On the odd index, whatever the sign of the number is the sign of the answer. Okay, we got to keep that in mind. So that's going to end up being just negative 6. Now, calculator style, just check this with the calculator. I want you to be able to do this for sure, because we're going to do some that don't work out to be nice numbers. But I just want to show you calculator as we go, and it's finally coming up and opening. All right, now to get the nth root, you have to use the math button. And then there's several different ones here. If you look down that first column, number 4 is a cubed root. That's only for cubed roots. It got its own spot, I guess, because it's used enough. Number 5 has an X in the index spot, so that would allow you to do fifth, fourth, any other number. I usually just use number 5 every time anyway. That way, I type in the index. So I'm going to pick number 5. And with the newest operating system, which most of you should have if you rented one from us, I know what that does. It's going to give you a box right here. We're going to put a 3 there. And then I press the right arrow key, and it puts me inside of the root. And I've got negative 216. And hit enter, and it cranks out negative 6. Works great on the ones that come out to be one nice number. That doesn't work so good when we have something left over, like maybe it was the third root of 432. That doesn't work out as nicely. It'll give a decimal answer, and we don't always want a decimal answer. It won't come out to be something radical, something. Like it's like simplifying square roots, like square root of 8, 2 radical 2. That's the kind of ones I'm talking about that you can't get the exact answer perfect with the calculator. It's where you got to know the factor tree method from. So let's do example B. Let's do the n equals 4 and a is positive 81. So we're finding the fourth root of 81. 9 and 9. 3 and 3. So a pair of 3s, or a set of 4 3s. That's what we're looking for, not pairs, because we got a fourth index. Index is 4, so we got a set of 4s. That's 3. Now here's where the even part comes back in. Remember when we did the square roots of numbers? Like if we were solving an equation, the square root of 25, what did we put in front of it? Positive or negative. Because you could get positive 81 if all 4 of these 3s were negative 3. Negative 3 times negative 3 times negative 3 times negative 3 is also positive 81. And so that's where we're going to get that plus or minus from. Even index, plus or minus. Odd index, whatever the sign of the number was, is the one we use. Even index, we're going to use pluses or minuses. Both, okay? Now, again, you could type that straight into your calculator. Since this one works out to be a nice number, you hit math, use number 5. It's the fourth root of positive 81. Hit enter, and I get it just tells me 3. We have to know that it's plus or minus 3. You just got to remember that. It's not going to tell you both of them. All right. N equals 5 for A being negative 64. Okay, so what's the index? 5. So that's the number that goes right there of a negative 64. It's an odd index, so that means the negative is okay or not okay. It's okay, and that means the answer is going to be what? A negative something, okay? And we're going to work that out. So if I did the factor tree for 64, it'd be 8 and 8, 4 and 2, 4 and 2. Get a little extra space here. 4 is 2 and 2. A lot of 2's there, but we're looking for a set of how many? Set of 5. 1, 2, 3, 4, 5. There's 5 2's. So that's the 2 that comes out. What's not part of that set? This 2 right here. So what's left over is the fifth root of 2. So it's a negative 2, fifth root of 2. So there would be a. Now if you tried to do this on the calculator, it's not going to work out too nice. It'll give you a decimal answer. Should. Yeah, negative. Yeah, it's a. That's the decimal approximation for that, but it's not the exact answer. Know how to get a decimal approximation. There's going to be times where we need that, but also know how to get the exact answer because there's going to be times when we need that as well. Okay, it just takes Factor trees and counting what's the index. And make sure you count that number. If the index is 5, you count for a set of 5. Index is 3, you count for sets of 3. Okay. Let's go to rational exponents and get a little work in with those. So rational exponents. If something is rational, what does it mean? It's written as a ratio, which we normally write ratios in math class as fractions. Fractions as exponents. Okay. Now, if you had some base with an exponent with the fraction m over n, that is the same thing as a root with the denominator being the index and the numerator being the exponent on the inside. Okay. The denominator is your index. The numerator is your exponent on the inside. Okay. So we're going to work with that idea to try to simplify some things. Okay. Let's look at a few problems here and kind of do some manipulations of stuff. So we're on example D. 16 to the 3 over 2 power. Using exponent rules, I can look at that and say, oh, well, it's actually 16 to the 1/2 to the 3rd power. If I think about the rules for exponents are, if I multiply it 1/2 times 3, isn't that 3 over 2? That's the same thing. So what I'm doing is taking the numerator out here. Or better, I think the more logical thing here is to go, oh, well, that's the square root of 16 to the 3rd. Both of these are the same thing. And I write this one because you're going to see that sum. This is what I want you to do. So I'm going from 16 to the 3 over 2 and turning that into 16 to the 1/2 and then the cubed root, and then cube that. That's taking the numerator just out to the top, outside. That's all I did. Okay. These two things are the same as that. The square root of 16 to the 3rd power. Okay. And then we want to simplify that. Okay. So what can we do to simplify that? We can think, okay, 16 cubed is really 16 times 16 times 16, right? And then I could do a factor tree from there on the 16s. 4, 4, 2, 2, 2, 2, 4, 4, 2, 8, 2. Getting bored here. And what am I? How many am I looking for in a set? 2. Because I'm doing a square root. 1, 2, 3, 4, 5, 6 sets of 2s. Plus or minus. That's 2 to the 6th power. 64. Now, if you don't know your exponent rules, you need to learn them. But everything we're going to be doing is related back to exponent rules. Where it gets a little bit more complicated and where that second step there, where this comes into play and is helpful, is when you start throwing a negative exponent in there. So we've done negative exponents before. Cover those in Algebra 1. 32 to the negative 3/5. So when I look at that one, I'm thinking I can do this. But that negative exponent causes a problem doing that, because putting a negative exponent inside of a radical doesn't really, it complicates things. It makes more stuff fractions instead of getting rid of the fractions. So what I like to think about here is think, oh, well, that's actually 32 to the 1/5 to the negative 3. So that really is the 5th root of 32, all to the negative 3 power. And the 5th root of 32 is an easy problem. The 5th root of 32 to the negative 3 is not an easy problem. This is easy. This is not. So we've used an exponent rule saying, okay, if the numerator's here, I can just throw it out to the outside and change that to a 1 over whatever. And then this becomes a 5th root. And then I do the 5th root of 32 the same way we did examples A, B, and C. I break down 32 as 8 and 4, 4 and 2, 2 and 2, 2 and 2. So there's 1, 2, 3, 4, 5 2s. So that's actually just 2 to the negative 3rd power, which is really 1 over 2 cubed. Remember, negative exponents from Algebra 1. A negative exponent, to change its sign, you move it to the bottom. And then what's 2 to the 3rd power? 1 over 8. Now, with a calculator, these that are working out nice, you can actually, go 32, the caret symbol over there on the right to get the exponent, and then type in negative 3/5. And it cranks out this decimal, and I can hit math and enter to see if it'll turn it into a fraction, and it does. That's great as long as it's a nice number. Not so great if it's not a nice number. So, you can try that first if you want to. And if it works, great. If it doesn't work, then you got work to do. Okay, so keep that in mind as we go here. So let's look at this one. 9 to the negative 3 halves. Go easier, maybe on this one. So if I think about that in terms of, I've got a negative exponent and I want to try to do this without a calculator first. I'm thinking, okay, that's 9 to the 1/2, and then throw the numerator to the outside, so negative 3. What's the 1/2 power? What root does it turn into? The index is a 2, so it's a square root of 9 to the 1st, which is just 9. And then that all gets raised to the negative 3. What's the square root of 9? 3. So we end up with 3 to the negative 3, which is actually 1 over 3 to the 3rd, which would be 1 over 27. So when they work out to be nice numbers, it's not too bad out of that. Doesn't always work out to be really nice numbers, and we're going to see that in the next couple of sections as we start adding in some variables. This first section, most of them work out to be really nice numbers because they're trying to just get you to understand converting back and forth between roots and rational exponents. That's what we're really trying to bounce back and forth here. That's going to help us, especially when we get into Chapter 7, which I was actually going to do Chapter 7 next and decided not to. Decided we needed this first because this comes up in Chapter 7. Doesn't come up much, but it comes up just enough that you would not know what to do. So thought, well, we better get this in before we do that, even though we don't have time because days are getting short. Let's look at these, and I want to evaluate. These are the ones you don't miss these on the quiz or on the test. It says evaluate with a calculator. Don't miss these. They're too easy. Don't miss them. 4 to the 2/5. And let's round. I'll tell you what to round to on the quiz and test. Round to 2 decimals. If we want to get technical, 2 decimal places would be the hundredths. 2 decimal places, hundredths position. So we are getting a decimal approximation. The reason we're going to get a decimal approximation is because this is actually 4 to the 1/5 squared. And 4 doesn't break down to be a nice number that's got a 5th root. So it's going to, it doesn't simplify really at all for us. So getting the decimal approximation is really about the best thing that we can do as far as doing anything with this. So we just do 4 raised to the 2/5. And going 2 decimal places, we look at the 1 that's after the 4, and it tells us to keep the 4 as it is. So it's 1.74, and that's our decimal approximation before that. Reason being, we need that because this doesn't simplify. You break a 4 down, it's 2 times 2, and there's not a set of 5 of those. So that's one of the reasons we would need that. 64 to the negative 2/3. And we're going to get a decimal approximation for that. So just go to your calculator and straight plug in 64 raised to the negative 2/3. Go 2 decimal places. So what's this round to? 0.06. If you don't round correctly, I'm going to mark it wrong. Okay? You've got to be able to round correctly by this point in your educational endeavors. If you don't round it correctly, I will count it 100% wrong. Okay. Is that one dead? Okay. I'll try to get some batteries put in. All right. 4th root of 16 to the 5th. What is that written in rational exponent form? If I wanted to write that as 16 to some fraction exponent, what's the fraction? Good, 5/4. That's how I type these in the calculator. I generally don't use that nth root button because it takes too long to get there. Like if I'm going to the calculator to type that in, I don't want to have to hit math and then number 5 and then type it in. I just think, oh, that's 16 to the 5/4. And it's the same number, 32 on this one. This one worked out to be a nice number, and that's okay, doesn't it? Technically, it would be 32.00. We go 2 decimal places. In a science class, that probably is important to know that it's 0.00. A math class, it's 32. Doesn't really change anything, but in a science class, it could be important. Cubed root of negative 30, all that in parentheses squared. How could I write that as a base with an exponent? Just to kind of get the back and forth. What's the exponent? Not negative 2/3. Just 2/3. Yeah, the negative is on the 30, so that's just positive 2/3. That's the same thing. Whichever way you type that in the calculator doesn't matter. It gets you the same answer. I'm just trying to get you to see that connection, to go back and forth between roots and rational exponents, because that's going to save us a little time, a little effort, especially when we go to solve equations in just a minute. Okay, so decimal approximation for that. So negative 30, and it is important to use parentheses. It is important to type in a 30 instead of a 3, because if you don't, there we go. And then 2/3. Rounding that to the proper place, 9.65. So the reason that's 9.65 is if you look at the 4, it's less than a 5, so you keep that the same. If that number, the third number is a 5 or bigger, you go up 1 with just that one. Don't change the other, just that one. Unless that's a 9, and then it goes up again. All right. Let's look at solving some equations using higher powers. We've done some polynomials of higher powers. We're not going to get into anything that complicated on this part. These are more simple equations, but it's using the rational exponent idea to do this, or the nth root to do this. So what letter are we on? Okay. Solve. 4x to the 5th equals 128. Okay. So to solve this one, or any of these problems, you want to get the part that has the exponent by itself. Okay. So the exponent is on what? The 5. And that's all it's on. So we need to get rid of that 4. How do we get rid of that 4? Divide by 4. X to the 5th, and that'd be 32. Now, here's where you got options as far as how to solve. To undo squaring, you use what? A square root. To undo a 5th power, you'd use a 5th root. On the left side, get an X. Now, here's where that plus or minus comes back in. Is that an even index? No. So that means we're going to use the sign of whatever that number is. So the positive 32 is what we got in there. So our answer is going to be the positive one only. If it's an even index, then we got to do plus or minus when we work these out. Okay. So what's the 5th root of 32? Works out to be a nice number 2. If you do that, we've already done that once today already. Or you could type that into your calculator and try it. So it ends up to be 2 out of that. Let's go a little bit more difficult. And let's do 21 is what it's equal to. So what has the exponent on this problem? X minus 3. So that part's by itself. And it's important that you get that part by itself first. And then we get rid of that exponent. So what undoes a 4th power? A 4th root. But that's what kind of index? Even. So if it's an even index, that means it's plus or minus the 4th root of 21. And this side is just x minus 3. We've gotten rid of the 4th power by using a 4th root. So it just takes that away and just leaves you what's inside, the x minus 3. And now we would try to simplify the 4th root of 21. If I break down 21, it's just 7 and 3. There's nothing else. There's not a set of 4 of anything. So if I want the exact answer, I'm just going to leave it the 4th root of 21. And then get x by itself. How do I get x by itself? Just add 3, right? So that's going to be x equals 3 plus or minus the 4th root of 21. If I need the decimal approximation, I'm going to split it apart and do 2 of them. And I would just go to my calculator and put that in there. There's going to be times I'm going to ask for an exact solution. There's going to be times I'll ask for a decimal approximation. Be able to do, if you can get the exact, you can always get the decimal, right? Because it's just typing it in the calculator. So let's type those in. 3 plus the fourth root of 21, that would be 21 raised to the 1/4 power. That's how I type those in. I get 5 point, let's go 2 places like we did before. So we look at the 0 and it says leave that alone. So that's 5.14. And then do the minus. So 3 minus the fourth root of 21. And if you want to type in, go hit math and go to that X root button, you can do that and it'll get you the same exact answer if you type it in correctly. But to me, it's just so much quicker to type it in that way using the stuff we know. So now what's this one round to? 0.86. The 9 is bigger than a 5. So it means this 5 goes up 1/6, so 0.86. Used to not have to worry so much about rounding or teaching it anyway. Most people knew how to do it. It's over the last 10 years I've seen it go where folks can't round anymore. I don't know why. I don't know where it got lost at. Before high school anyway. So
pardon the interruption. The softball game that was scheduled for Middleton has been canceled today, so students should stay in class. It is possible that we move the game here this afternoon, but that is not known for sure right now. Thank you.
all right, good deal. All right, let's look at this one. 1/4 x to the third is equal to 2. Pick a number. What part has the exponent? Does the 1/4 have the exponent? Just the x. So we need to move the 1/4. How do we move that 1/4? Divide by it or multiply by the reciprocal 4 over 1, technically. Those cancel. There's x cubed is equal to 8. And now how do we solve that? What root do we use? Cubed root. Third root, cubed root, same thing. Do I need a plus or minus on this one? Why not? Because it's an odd index, so that's why I don't need the plus or minus. What's the cubed root of 8? Do we know that one? 2. And we don't have to get a decimal approximation for that. We get the nice number. Let's do this one. X plus 5 to the 4th power equals 16. X plus 5 to the 4th power is equal to 16. Is the part that has an exponent by itself? Yes. So how do we undo the exponent? Take it's a 4th power, so the 4th root undoes it, right? What do I have to add to it? Plus or minus, because why? Because it's an even index that I put in the problem. If I put an even index in there, I've got to do plus or minus. Does anybody know the 4th root of 16? It works out to be 2. If you type that in your calculator, check it. If it gets a nice number, then use it. It's 2. So we have x plus 5 is equal to plus or minus 2. So we set up x plus 5 is equal to, well, hey, let's just go ahead and solve it from there. That's minus 5. So x equals negative 5 plus 2, and x equals negative 5 minus 2. It'd be negative 3, be negative 7. Works out to be 2 nice numbers for that particular problem. Yeah, we can do it. Now we're doing the second section as well. There's some exponent properties as well. So that's section 6.1. We're going to go ahead into 6.2. You got a work day tomorrow over 6.1 and 6.2. 6.2 is more about exponent properties and doing some things with exponents and working with rational exponents as well. So we're going to try to go through some of this. All right. Going through the properties of exponents. When you multiply two things that have the same base, what do you do with the exponents? Add them. When you have something and an exponent on the outside, what's the rule there? You multiply them. If you're dividing, what's the rule? Subtract. Top minus bottom. If you've got a negative exponent, so like a to the negative m, you can change that to a positive exponent by putting it on the bottom. If it's negative on the bottom, you can change it to a positive by moving it to the top. So that works back and forth there. Other property might be, you got a fraction, something with an exponent here, something with an exponent there, two different ones. So you can't do the subtraction rule because the bases are different. But this exponent on the outside goes back to this rule. You multiply, but it multiplies to every exponent on the inside. So that's a to the mx over b to the nx. And we're gonna do some examples where all of these are kind of thrown in there. So we gotta know or remember these particular rules as to what's going on with our exponents. Okay. These rules apply no matter what kind of exponents we have. In Algebra 1, you only work with integers as exponents, like x squared times x to the fourth is x to the sixth. In this particular chapter, we're going to work with fraction exponents. So we may have to add fractions with our exponents to simplify something. So we're going to get kind of involved in that and see what's going on. So let's simplify is the name of the game here. Example A. X to the 1/4 times x to the 1/2. X to the 1/4 times x to the 1/2. The bases are the same, and they're multiplying. So what's the rule for the exponents? You add them. 1/4 plus 1/2. I don't care how you add that. If you use the calculator to do it, fine. If you do it in your head, even better. Whatever you got to do to add and subtract, or add those exponents. 1/4 plus 1/2. So that'd be 1/4 plus 2/4 is 3/4. That's what we're doing. It's part of what we're doing anyway. Not everything we're doing, but it's part of it. Got to get us there. Okay. If you had, maybe you got x to the 1/2 times y to the 1/3, all that in parentheses to the second power. What's the rule for this exponent? What's it do to these two on the inside? Multiplies, because it's an exponent on the outside. That's this rule right up here. That's that rule right there. It multiplies. So that would be x to the 2 times 1/2 is 1, right? So that's x to the first power. 2 times 1/3 is 2/3. And you've simplified. You've taken that exponent rule and worked it out. Not much happening there, but it is what we're dealing with here. Let's say we had x to the 5th times y to the 5th, or let's make that y to the 10th to the negative 1/5 power. So what's the rule on this one? Fraction exponent's on the outside this time. But it's still the same rule. You still multiply straight across. So it's 5 times negative 1/5, which would be x to the negative 1. And then 10 times negative 1/5 is how much? Negative 2. And then we can't leave a negative exponent in our answers. You remember that from Algebra 1. You know, we never left negative in our answer unless we were doing scientific notation, and that's definitely not what this is. So we want to fix those. So how do we fix negative exponents? Move them from where they're at to the denominator, or if they're in the denominator, move them to the numerator. So these are in the numerator, so they're going to go to the denominator and become that. X, technically to the first power. I don't ever write the 1 exponent. You can. It doesn't count against you if you do. And then y squared on the bottom. Okay? Not too bad. Not too bad. That's good. Two to the negative 6 times x to the 9th, all to the negative 2/3 power. Again, same rule. So I'm doing several examples of this rule because it gets interesting when you start changing the sign of what's positive and what's negative there. So what happens there with these when you do those exponent rules? Be negative 6 times negative 2/3 would be 2 to the positive 4, and then x to the negative 6. Now, which one of those has to move? The x has the negative exponent, so it's the only one that moves. So 2 to the 4th stays up top, and x to the 6th goes to the bottom. And what's 2 to the 4th power? 16. So we could go ahead. That's not a really big number, so you could go ahead and work that out. On quiz and test, I'll tell you whether or not to work the number out. If it's a small number, we're going to work it out. If it's like 2,586,253, we're probably not going to work it out. It's too large. Doesn't do you any good to work it out. The exponent rule is what we're after here anyway. Okay. So, example E. Say we had x over x to the 1/3. What's the rule for those exponents? Subtract, because it's division, right? What's the exponent on the top x? It's 1. So 1 minus 1/3. 1 minus 1/3 is 2/3, right? You can leave it that way. X to the 4th over X to the 6th. Those are still rational exponents. They just have a 1 in the denominator. What's the rule? So 4 minus 6 would be X to the negative 2. But we got to fix that. 1 over X squared would be the final answer. And it makes sense that it would be 1 over X squared. Where are the most X's at? They're in the bottom. So your leftovers should be at the bottom anyway. So that works with that. Okay. Let's look at it at kind of a tricky thing. When they start throwing some numbers in there, some tricks can happen. 42 to the 1/3 over 6 to the 1/3 squared. There's some pretty cool stuff that can happen here. What do you notice is the same on this fraction? The 1/3 exponent. So what we can do here is manipulate that into this fraction where we have 42 over 6 to the 1/3, and then all of that is squared. Why would we want to do that? Yeah, 42 over 6 simplifies to be 7. And we are simplifying, so that's the idea here, is that that becomes 7 to the 1/3 squared, which is actually 7 to the 2/3. So that's the simplifying step. If you see different bases that have the same exponent, then you can do some stuff like that. That's what you got to look for, is you look for the same base first to do those rules. But if the bases are different, look to see if they have the same exponent, and then that opens up some ideas for simplifying, especially when it's numbers. They're going to throw those in there. Kind of makes it an interesting idea. Okay. All right. Still, the instructions are still simplify. Problems are going to look a little bit different. Now remember how to multiply radicals? How do you multiply? How do we multiply? It's like, this is not an example for our notes. It's just a side example. If I had square root of 3 times the square root of 6. Why? Yeah, you multiply the inside, so it's square root of 18. This is no different. It's the same root. It's just it's a third root instead of a square root. 12 times 18 is on the inside. So figure out what 12 times 18 is. 216, which is a good number. And is the cube root of 16 or 216? Didn't we do that in section 1? It was 6, wasn't it? Sorry, I remember everything. Well, not everything. Only things that don't matter. Like I can't remember to get a jug of milk when I go to the store. Yeah, came in today. It's not for me, it's for my son, but I think I should have ordered myself one because it's really relaxing. That helps me stay on task. I don't know why. Helps me not think about how hot it is in this room. Sarah's up here in a jacket, Emily's back here in a jacket. You guys got on long sleeve shirts. I got on long sleeve shirts. That was a bad idea today. Juan's got on the jacket. Juan, you feel okay? Everybody was picking on Juan when he came in. Juan, you feel okay? Juan, you feel okay? Fourth root of 80 over the fourth root of 5. Same root, right? So this is kind of like example G. If they're the same root, I could do this. Why would I want to do that? because 80 is divisible by 5, right? So that simplifies to be 4th root of 16, which is always thought Harry Potter should have a spell. Simplify. And it would reduce them down to, I don't know. Babies aren't real simple, so I guess maybe a spinner or something like that. That would have been a good Harry Potter spell. Simplify. I wish I had that wand to do all this work instead of me having to do it. It'd be nice. Y'all figure that out. Mark that out for us. Cube root of 135 times the cube root of 10. All right, good. Now, we got to see if we can simplify that. So that's 135 and 10. Be 5 and 27. And 27 breaks down to 9 and 3. 3 and 3. 10 is 5 and 2. So we're looking for sets of how many? 3. 1, 2, 3. There's only 2 5s and then a 2. So there's a 3 on the outside. What's left on the inside of the cube root? 2 5s. 5, 5, and 2. 25 times 50. And there's a simplified version of that. Skip those. Yeah, it didn't come in today. It's supposed to come in later this week. Yeah, I'm excited. Yeah, is it loud? Because I didn't know how loud they were. Oh, okay, so annoying enough, I guess. All right, let's look at this. Square root or 3 radical 5 plus 7 radical 5. Adding. What has to be the same for us to be able to add them? The under the thingy stuff. It means under the what? The radical. The radical has to be the same for them to be like terms. What part do we add together? The outside the thingies. So 7 plus 3 is 10. Radical 5. So that's algebra 1. We're going to do bigger roots than that. Let's say we had the 4th root of 10 plus 8, the 4th root of 10. If there's nothing in front, what's really in front? 1. So that'd be 9 4th root of 10. We would need to see if we could simplify that 4th root of 10. It doesn't, but we would always look to see if we could out of that. Cube root of 54 minus 6 cube root of 2. Right off the bat, it doesn't look like anything can be done. But what should we always try to do? What are the instructions? Yeah, we could break down the 54. And this is where doing it without the calculator is really very important. So that'd be 54 would be 9 and 6, 3, 3, 3, 2. A set of 3. So that ends up being 3 radical 2, or 3 cube root of 2, minus 6 cube root of 2. Which ends up being what? Negative 3 cube root of 2. they get fancy with this stuff. And write it like that. And what? Right, because 8 to the 1/5 is really just what? The fifth root of 8. Yeah, the radical with the fifth root of 8 is all that 8 to the 1/5 really is. So that doesn't change the game at all, really. 12, 8 to the 1/5. I would be fine if you wrote it like this, if it felt more comfortable to do that. The fifth root of 8. Either of those would be acceptable answers for me. If you had a multiple choice type option, know that both of those are possible. They may write it as 1/5 power, but the answers may also be written as the fifth root. So be able to bounce back and forth between those two. Let's get to some that are maybe a little bit more difficult. I don't know that this one is that difficult, but at least it's different. 5 to the 1/3 plus 40 to the 1/3. What do we do? Does it make more sense if it's written like this? Does that make you understand what to do better? That we should work to do what? Get what the same? The radical stuff the same. This is saying the same thing. If it makes more sense to you to write it that way, then yes, you can write it that way and work it. That's fine with me. Understand, though, that they are the same problem. The 1/3 power and the third root, cube root, are the same. 40 breaks down, though, into 8 and 5, 4 and 2, 2 and 2. So there's 3 2's. So this is really 5, or the cube root of 5 plus 2 cube root of 5, which ends up being, there's a 1 there, 3 cube root of 5. How else could that be written? Three times what? Think about example N, how it's written. The third root of 5 is 5 to the 1/3. Be able to bounce back and forth in what form it's written in. That's where we really understand, if you understand what's going on, is bouncing back and forth between the notation. We've got several examples today, but none of them take a ton of time. So I got a lot of examples just to give you more and more things to go by so that you've seen several types of problems. So this one, I'm going to put a variable inside. And I'm going to show you how I like to do these. I generally do not do them with the roots. I like to change them to rational exponents because I think it makes it easier as far as the letters go. Because this is really 64 y to the 6th to the 1/3 power. And then I think, okay, 64 is 8 and 8, 4 and 2, 2 and 2, 4 and 2, 2 and 2. So 64 is really 2 to the 1, 2, 3, 4, 5, 6 power. Yeah, add it, 240. Work day tomorrow, so no worries. And then y to the 6th. So what I've done is I've factored 64 into what it is. It's 2 to the 6th power. And now I have this problem where it's a simplifying problem like we did before. What do I do with this 1/3 and these exponents in here? I multiply them because that's what the exponent rule is. So 1/3 times 6 is 2. So that's going to be 2 squared, and then y squared. What's 2 squared? 4. And you've simplified that using rational exponents instead of roots. I like doing the rational exponents because it works, the variables work a little easier that way. Because 1/3 times 6 is easier than thinking, okay, third root of y to the 6th. That doesn't make as much sense as 1/3 times 6 does to me. So this is how I like to work them. If you don't like that way, and you see a video on YouTube that says do it a different way, then you're welcome to use that way as long as you get them right. I'm not opposed to that. My way is not the only way. Anybody ever tells you that, they just don't know another way. I don't know if mine's the best way. It's the best way for me. It's the way I understand it the best. I don't know if it's the best way. Depending on how your brain works. And we all know my brain does not work like everybody else's. I've been here long enough to know that. So here we have a cube root of 27 p to the third q to the 12th. Again, I think of that as 27 p to the third q to the 12th to the 1/3 is the way I think about that. And then I break down 27 to be 3 cubed p to the third q to the 12th. And that's all to the 1/3 power. And then all I got to do is multiply exponents. So once I get it rewritten, multiplying it, the exponents is all I have to do and simplify. So 1/3 times 3 is 1, so that's 3 p, and then 1/3 of 12 would be 4, and I've simplified. To me, that makes a lot of sense. It doesn't have to be done that way. There are other ways. If some of you, if you ask Coach Mack how he does it, he's going to do it a different way than that. If you ask Miss Ross how she does it, she's going to do it a different way than probably either of us. She's going to have some weird name like Trick or Treat or something like that for what she does. And, you go visit every house or something. I never had Miss Ross for a math class, so I don't know her terminology. I just know it's different. And by different, I mean weird. And I'll tell her that to her face, We've been friends for a long time. Her daughter and my wife were really good friends growing up. They played ball together and everything. So we've known each other a long time. All right, let's simplify this guy. Now this is where I think my way starts kicking in really, really nicely. Because the fourth root of all that junk inside a fraction there doesn't look real nice. But if I write it as m to the 4th over n to the 8th to the 1/4 power, what's the rule for the exponents? What do you do with the exponents to get that? You multiply. 1/4 times 4 is 1. 8 times 1/4 is 2. And you got your answer. That's where I think it starts really coming through well. Let's do another. 5th root, x to the 10th over y to the 5th. Turns it into a 1/5 power. Then multiply. 10 times the 5th, x squared, y to the 1st. You're done. Let's put some numbers in there in this fraction. 14 x y to the 1/3 over 2 x to the 3/4 z to the -6. That's a z in the bottom. There, this is 2, this is Z. And we want to simplify that. And when we say simplify, I mean, can't have negative exponents. Any numbers that'll break down, we break down. And any variables with exponents that can be followed by an exponent rule, you do that. So, X on top and X on the bottom. What's the rule? What am I going to do with those two? Besides close up the end of that horn. Makes algebra easy when they're playing music in the background. All right. This is X to the first over X to the 3/4. What's the rule for exponents when you've got division? Subtract. 1 minus 3/4 would be 1/4. Is there a Y on the bottom? No, so there's nothing to do with the Y, so it doesn't change at all. So it's just going to be Y to the 1/3. So what does the 14 over 2 turn into? It's just 7. And then the Z to the -6 down here, we need to fix that. So where does it go? Up top. What's left on the bottom? Just a 1. Nothing else is there, so it's like a 1 is there. So that's our final answer there. Just that. It's technically that over 1, but you don't have to put the over 1. Five more examples, guys. We got it. We can do this. We can do this. We'll get through the whole alphabet in this section. I'm excited. I don't know if that makes you excited to get through all the way through Z and then plus 1. Are we? I'm on. I did U. I did V. W, X. W. U, V. Did I? It's okay. It doesn't matter. I'll do 2 more examples at the end then and get P and Q back in there. How about that? 6x y to the 3/4 over 18 x to the 1/2 y to the 1/2. Ooh, fun one. Got it. Exponents everywhere. I'll do the easy part, 6 over 18. Y'all do the other part. 1/3. I got that. Accomplished. What do you do with the x's? Subtract. 1 minus 1/2 would be, where does it go? Top or bottom? Top. Always answer, when you do the subtraction, answer always goes to the top and then we fix it. And then y's, we got 3/4 minus 1/2. 1/4 where? Top. And then do we need to fix any of that? No negative exponent to work on, so we're done. That's it. All right. 56 a to e to the 3/4 over 7 a to the 5 over 6 b c to the -3. Fun. All right. 56 over 7. The 8. Where's that 8 at? Top or bottom? Top. We may have a denominator. We don't know yet. So a to the first and a to the 5/6. What do we do with those two? Subtract. So 1 minus 5 over 6 would be 1 over 6. What about the b's? Be a -1/4, wouldn't it? B 3/4 minus 1 would be -1/4. I always put my answer in the top and then fix it. That's the best. I think that's a best practice. And then C's, What does that go? It goes up to the top. Technically, there's a 1 in the bottom, but when we fix everything, there's going to be b to the 1/4 in the bottom. We should just go out on the lawn and yell multiplication facts at them. They'd stop. We start yelling. We'd sing the quadratic formula to them. That'd be good. They'd go in then. Do that. All right, 1/5 square root of w plus 3/5 w to the 1/2. That doesn't look like it's the same. Is it? It's not? Yes, it is. The 1/2 power is the same thing as what index on the root? Square root. Square root and a 1/2 are the same. So they've written it mixed up. Pick one of the ways of writing it. Since we're in the rational exponents chapter, this is how I would write it. And then the roots are the same, or the like terms here. So we have 1/5 plus 3/5 is 4/5. Either of those ways of writing the answer would be correct. 4/5 w to the 1/2 or 4/5 square root of w is the same. Three x y to the 1/4 minus 8x the 4th root of y. Are those like terms?
Yeah.
Yeah, they are?
Yeah.
Sure? Yeah. What makes them like terms? The 4th root and the 1/4 interchange, and they both have x's on the front there. So when we put these together, it's going to be what? -5 x y to the 1/4 or -5 x 4th root of y. Either of those ways of writing the solution would be correct. I skipped P. I did skip P and Q. We got to do P and Q. Yeah, we did. We didn't do the whole alphabet if we don't do P and Q. I had one more written down anyways. Cube root of 2z to the 5th minus z cube root of 54 z squared. Fun one. What needs to happen here? We need to simplify that 54 there in the cube root. So 54 breaks down 9 and 6, 3, 3, 3 and 2. So a set of 3 there. So it's going to be 3 on the outside. What comes out on the first one? Z to the 5th on the inside. It's a cube root. If I think about that, it's z to the 5/3. How many times 3 go into 5? One time with how many left over? 2. So that's really 12z cube root of 2z squared. Because the 1z comes out because 3 goes into 5. Or, excuse me, 5. Yeah, 3 goes into 5 one time. The squared is left on the inside because there was 2 left over. And that's how that's simplified. On this one, a 3 is going to come out with the z that's already there, and it's going to leave a 2z squared on the inside. So that's minus 3z cube root of 2z squared. All the z's and 2's there. So the final answer would be 9z cube root of 2z squared. That's a tough one to finish on, but you don't get too many of them like that. You get more of them like what we're doing there before. All right, so tomorrow's a work day on page 417, 15 through 57, odd. That's section 6.1. 6.2 is on page 424, 3 through 65, odd. Looks like a lot, but really these problems are not long. Most of them aren't. I mean, we went through almost, alphabet almost twice here today. So not an incredibly long set of problems. There's several problems, but they're not long problems each. So.